Series resistance. Nothing too mind-blowing about this. When resistors are connected end to end, as shown below, they are said to be connected in series, one after the other. Okay. We tend to make designations of, put a number by it, so R1, R2, R3, R4, R5 and so on. You might see RL for what's considered to be the load of the circuit, okay, and then we might even just put a resistor symbol to designate a particular load like a motor or a heater. We just draw a resistance symbol because that's what we're interested in, its resistance. Calculate total resistance, or the equivalent resistance of a series circuit, using the formula RT for R total is equal to R1 plus R2 plus R3 plus 3 dots R to the n. All that means is any number of resistors that are all connected in series. Yep. What we get, and we'll look at it in a little bit more detail later, is when we've got a series connection, one current, the same current, flows through all of them. That's the thing with current. Whatever we put in this end has to come out that end. It's got nowhere else to go, and we don't have any leaks. Yeah. No. Voltage drops. More about that. We get on to that next week. Okay. Parallel resistance. When resistors are connected across each other, as shown below, they are said to be connected in parallel. Again, we label them R1, R2, R3, R4 and so on. Now, this is where it gets a little bit more tricky, because there are a number of ways for calculating parallel resistance. First of all, well, there's three methods. First of all, if you have, like the circuit up there, two resistors only, and it doesn't matter whether they're different values or not, you can use this formula. RT is equal to R1 times R2 divided by R1 plus R2. Often called the product over sum rule. Product meaning multiplication, sum meaning add together. And that will find the total resistance of two resistors, and it doesn't matter whether they're different values or not. Okay. One thing you should remember is what you're doing when you find the total, when you do that calculation, is you're finding the one resistor value that you could replace both of them with. So you could take R1 and R2 away and put a single resistor equal to RT in that circuit, and the same current will flow in these 2 points, here and here. Yeah. And more about that as we move on. If you have three or more different resistors, so three or more, up to any number of resistors, all connected in parallel with each other, you use this formula. RT is equal to bracketed term R1 to the minus 1 plus R2 to the minus 1 plus R3 to the minus 1 plus Rn to the minus 1, saying any number, close the brackets, and then the whole lot to the power of minus 1. You have a button on your calculator, x to the minus 1, reciprocal button. Okay? Yeah, you may have seen it in that form, Don, but you don't like fractions.
I prefer it like kind of 1 over that. Power of minus 1.
Do you?
Yeah.
Oh, okay. Yeah. I'll explain to you on another slide why I've migrated to doing it that way. You may have seen that formula like this. 1 over R1 is equal to 1 over R2 plus 1 over R3 plus 1 over R4. Yeah? And when people do that calculation, what they tend to do is forget that you're finding out what the reciprocal of resistance is. When you find the value of that bit, you need to do 1 over the answer to get the final result. I used to have a lot of misunderstanding about that, and I found that the students I was teaching got on better with the R to the -1 formula. But you can use whatever. I don't care whether you use that version or the other one. If you wanted that in R equals form, you'd have to put it like this. R is equal to 1 over all of that lot. And so on. Okay? Yeah? Also, I find if you're given a problem where you've got one of the parallel resistors missing, given the total, the 1 to the power 1 formula is a little bit easier to rearrange. But anyway, going back to that, that's the second way, is to use that formula in either of those two formats. Because that's all to the -1 means is 1 over, isn't it? Yeah. The third way is if you have any number of resistors that are all the same value, like 4 100 ohm resistors, or 250s, 360s, you can use this formula where the total is that one single value divided by the number of them that you've got. So if you connect 4 100s in parallel, your total will be 25. 266s will give you 33, and so on. Okay? So that's the whichever the single value of resistor is, divided by how many of them that you're connected in parallel. Skip back over that one. Right. Series and parallel combinations. So, if we look at that, we can have two general combination types. This is two resistors in parallel, connected in series with a third. Yep. Resistor. This type is two resistors in series that are connected in parallel with a third. All right. And they're the most basic combinations that you can have. We're going to find out we can have some more difficult combinations. If we call these R2, R3, and R1, R1, R2, and R3, what we have to do to solve them for the total is, in this case, we have to do a parallel on that one to find the total of those two together. Yeah. What we've then got is this circuit, and I tend to call that R1 and R23 to denote the total of 2 and 3 added together. We can then just add those two resistors together to find the total. In this case, we've got to find the total of those two added together. We then end up with a circuit that looks like this. R2, R12 in parallel with R3. And we do product over sum or one of the other rules on that. Find the total of those two. So the idea, the general idea is you're doing small parts of the circuit, trying to turn it into all series or all parallel. And then you got your final answer with the last calculation. You do it in stages. Yeah. So on the next page, let's imagine these are all 50. Where are we going to start? Yeah. Which two resistors you got to start with? Yeah, okay. So first of all, we go R1, 2 is equal to R1 plus R2, 50 plus 50 equals 100 ohms. Yep. So what we've done is said that 100 ohm resistor is the one resistor that would replace those two. Take those two out and put 100 ohm in there, we'd have exactly the same circuit electrically as far as the current flow is concerned. Next job. Product over sum on that 100 ohms and that R3. Yeah, so we can go R123 is equal to R12 times R3 over R12 times plus R3. So that's 100 times 50 over 150. 33 1/3 ohms. So that whole bit there, all of those three resistors could be replaced with one of 33 1/3 ohms. Yep. We know that one's 50 on its own. We ain't got to do anything with that. And these two are 50. So last thing, last thing, R56 is equal to, from what's the quickest one though? They're both the same. So you can do 100 over 2, because there's 50 over 2, sorry, there's two of them, equals 25 ohms. So now we've got a complete equivalent circuit, and that's replaced 25 ohms. Yeah? And so now we just add up all of those. We got a total. RT is R123 plus R4 plus R56. That is your 33 1/3 plus 50 plus 25 equals 108 1/3. Ohms. All agree? Yeah. So that's how you do it. Got to look. You've got to isolate pockets of all series and all parallel. The only formulas you got is that you've got a formula for all series, add them together, and you've got a formula for parallel, 3 versions of it. You cannot do the combinations in one go. Not yet, anyway. But there isn't a standard formula. You have to make one up out of the others. Okay? Eventually, we'll be doing some work at some point in the degree we need to be able to do that series parallel combination in one go, but not yet. Okay. Something else that's in your notes, and I just wanted to highlight, is a number of ways in which textbooks and websites are used to indicate the values of components such as resistors. None of which I've used in the circuits for the problems below. This is where a capital letter denoting the multiple is used in place of a decimal point. For example, a 2 ohm resistor being designated as 2R0, the R denoting that as the base ohms. 5.6 ohm resistor, 5R6. A 2.7K kilo ohm resistor, 2K7, with the K denoting kilo or 10 to the 3, and a 4.7 mega ohm resistor, 4M7. So it's quite common for that to be done on circuit diagrams. So I'm trying to introduce you to all those little things that you might come across. All right. So in your, we've got a problem here. Coil has a current of 75 milliamps. What is the resistance of coil? How much? That's just an Ohm's law and power problem. In your notes, on pages 13 and 14, that's the back 2 pages, there are 4 combination circuits for you to have a go at calculating the total resistance of. Again, the answer is in the brackets. Okay. Have a go. See how you get on. Let me know if you don't get the answer that's given.